lot of the stuff that can make distributed loads and centroids and joints tricky. So here's the example problem. Bless you. So you have a pin joint up in the upper left corner and a rectangular solid. That pin's supposed to be right in the corner. And then all the way in the exact other corner is another pin that slides in a slot. And this slot makes an angle of 30 degrees with the horizontal. And then there's a hole cut out of this rectangle, an inscribed circle. And this length is 2 meters. This height is 1 meter, and that's also the diameter of that circle. And then besides the weight of this shape, and the mass is 50 kilograms, there's also a distributed load on this half of the body. That comes up to a maximum value of 500 newtons per meter. And we want to calculate those reaction loads. All right, so when we get to the free body diagram, we're going to have to treat those distributed loads, the weight and the distributed load, as point forces. So we're going to have to figure out the centroid of that rectangular shape with the hole cut out of it, and we're going to have to figure out the centroid of that triangular distributed load. So let's do that first. For the rectangle, let's call the rectangle piece 1. And then the circle that we're cutting out of it, we'll call that piece 2. For each one of those two pieces, we need to know the area and the centroid. Well, one thing to notice here is that the reason we need that centroid is to know where the weight's applied. So we only need one of those components. Which one of those components don't we need if we're just applying the weight force? Because, you know, the weight is just down. Yeah, we don't care about the Y position, so we can save a little time. So I'm just going to do the X components. The area of the rectangle is 2 times 1, so 2 meters squared. The centroid is the middle of that rectangle, so that's just 1. The circle, the area is pi r squared for the circle. The radius, the diameter is 1, so the radius is half. So this is, you know, pi over 4. So that's about 0.785. And the x centroid of the circle. So I guess I didn't draw where my coordinate system is, but I'm thinking of the coordinate system over here. So if you look at the x centroid of the rectangle, you're going 1 meter from there to the middle. So the centroid of that circle, you have to go 1 meter to the right in the positive x direction to get to the left end of the circle, and then another 0.5 to get to the middle. So the centroid is 1.5. And now we're just going to do this as a subtraction. The total area, notice if you're subtracting a piece like this, the total area is going to be the outer area minus the inner area. So A total is 2 minus 0.785. So 1.215. And then the centroid of the whole shape is 1 over the total area, 1 over 1.215, times the quantity, area of the outer shape times its centroid, minus area of the inner shape, the subtracted shape, times its centroid, and you get a centroid value of 0.677. Okay, so this is one, since there's no material here and there is material here, that's going to move the centroid from the middle this way. Okay, so it's like over here somewhere. And now we have to figure out where that, the point force representing that distributed load acts. So for that triangle, I guess let's draw the coordinate system. And the triangle is this, where this is a meter and this is a meter. The length of this triangle then is 1 meter. The height, the maximum distributed load, is 500 newtons per meter. So the area of that triangle is 1 times 500 divided by 2, just the area for a triangle. So 250, and that's in newtons. You could get those units just by multiplying out the units for the distributed load and the length, because this is newtons per meter. And the centroid of that shape, again, since this force is just straight down, we only care about the x location of it. So that's going to be a third of the way from here to here, So this distance to the centroid of that shape is 0.33. So all the way from the coordinate system, this is going to be, 1.67, 1 2/3. All right, so now we can draw the free body diagram. There's a weight force that's acting from the centroid of the rectangle. The thing has a mass of 50 kilograms, so this is 490.5. There's a point force acting from the distributed load that has a magnitude of 250. The pin joint at the upper left applies an unknown force vector, so I'll call that RA vector. And then the pin and slot joint, if this is the slot, we know that that force is perpendicular to the slot. We know the direction of that force, but we don't know the magnitude, so I'll call that RB. For that force RB, could that come out positive or negative, or does it have to be positive? Either way, for a pin and slot joint. Okay, so now I'll write out the table. Rho force moment. I'll do my about point here at A. So for that force RA, the rho vector is 0. The force is RAX, RAY. And the moment is 0. And then for the weight force, so the rho vector, the x component of the rho vector is 0.677. What's the y component? Doesn't matter. Yeah, I put 0 or whatever. That we know that you can move it along its line of action without changing what it does. The force vector is 0, negative 490.5. Take that cross product and you get negative 332.07. Does it make sense that that moment produced by the weight force is negative? Yep, that's a clockwise moment. So, and then the distributed load, the 250. The x component of that is 1.6, I guess 1.667. I'll write it 1 2/3. What's the y component? Yeah, it doesn't matter. Yeah, 0 is what it would be, but you could put anything for that and it won't come into it. The weight force is 0, negative 250. Cross product is negative 416.75. And then the last one is that RB. The rho vector is 2 for x, negative 1 for y. This one, we know the direction, so we have to come up with a unit vector for that direction. So if it isn't apparent to you right away, draw the coordinate system. Draw a vector that's parallel to that slot, okay? Because the reference we have is from the horizontal to that slot. So I'm going to draw a vector this way. And we know that this angle is 30 degrees. And now we know that it's 90 degrees to get from that slot or that vector I just drew to this vector with the magnitude of RB. So this is 90 degrees. And so the angle that we want, theta, is positive 30 to get to that first red vector, and then another positive 90 to get to the next one. So 120. And the force vector is RB times cosine and sine of that angle of 120. So this is negative 0.5 RB, positive 0.866 RB. And if you take that cross product, you get positive 1.232 RB. Okay. We have 4 forces appearing on the free body diagram, 4 forces appearing in the table. So we know we have everything. So now write out the equations. So the first equation is the x force equation. RAX minus 0.5 RB is equal to 0. The y equation says RAY plus 0.866 RB is equal to 490.5 plus 250, which is 740.5. So this one says RAY plus 0.866 RB is equal to positive 740.5. You have to remember you're moving that constant over to the other side, so that's why it's negative in here, but if you move it to the other side, it's positive. And then the moment equation says 1.232 RB is equal to the sum of those two, but positive. So 1.232 RB is equal to positive 748.82. It's 3 equations for 3 variables. So we need an augmented matrix with 3 rows and 4 columns. So the first equation, RAX's, there's 1. RB's, there's negative 0.5. The other stuff is zeros. The second equation, RAY's, there's 1. RB, there's 0.866. Constant, 740.5. And 0 for the other one. And then the last equation, RB's, there's 1.232. Constant, 748.82. And zeros. And if you solve that, you get an RA vector of 303.9, 214.1, and an RB value of 607.8. Any questions about that? Okay, so that's it for centroids and distributed loads, and next time we'll get into the biggest topic in this class, which is structures.